had its origins here in this very chemistry department under the initiative of Istvan Marko and a few of his colleagues at the time. David Cole-Hamilton did his studies for his BSc and PhD in chemistry at the University of Edinburgh. And then, like many young Scotsmen, I joined this group as well, went out of Scotland. We seem to be very good at producing academics and sending them south of the border. He went, however, to a very distinguished laboratory as a postdoc. He went to join Sir Geoffrey Wilkinson at Imperial College, London, to start working on aspects of inorganic chemistry and homogeneous transition metal catalysis. He then got a job as lecturer and eventually senior lecturer at the University of Liverpool before he returned to Scotland in 1985 to take up the Irvine Chair of Chemistry at the University of St Andrews, where he served until 2014, and since then he's been an emeritus professor with a still very active research group in St Andrews. He served a lot of roles in chemistry, including the president of the chemistry section of the British Association for the Advancement of Science, chair of the Royal Society of Chemistry Edinburgh Committee, and a member of many committees, including years as president of the Dalton division of the RSC. In the UK, in Europe, he's been the representative on UChem's division for organometallic chemistry since 2005 and was president of the society, establishing UChem's as a voice of chemistry in Europe, representing more than 160,000 chemists from more than 40 member societies. He's been very active in the area of organometallic compounds, homogeneous catalysis and material chemistry, and he defines himself, I think, very reasonably as a committed European, a committed scientist who believes that chemistry holds the key to the future prosperity and quality of life for all. With these introductory remarks, David, it's my pleasure to introduce you and to welcome you to here to give you a talk on elements in danger. David Cole-Hamilton.
Thank you very much indeed, Bob. It's a great pleasure to be here today. I'm just going to share my screen so you can see what I'm doing. Yeah, it's a great pleasure for me to be back talking to the Royal Society section. I think it's my fourth visit, and I really do enjoy coming, and I'm very sad that I can't be with you each visit. Before I start, I'd just like to congratulate all those people for the various different awards. They've done fantastically well, and I wish them well. I'm going to talk about elements in danger or element scarcity. I'm going to talk about a new version of the periodic table, which was developed by the European Chemical Society last year to celebrate the International Year of the Periodic Table, which celebrated 100 years after Mendeleev first wrote down his version of the periodic table. The people who've been involved in making this periodic table are here. It was a task group which I led. And I particularly like to pay tribute to Nicola Armaroli because he had a lot of the ideas that went into this periodic table. Robert Parker is the General Secretary of the Royal Society of Chemistry, and I'll mention him again later because he had a very important contribution to this periodic table. The person, however, I'd really like to pay tribute to is Suzanne Issa. Suzanne works in print and design in St Andrews, and she is the person who actually drew the periodic table. I sat beside her saying, move this line there, move that line there, change that color, change this color, move that there. And she was wonderful. She did everything. So really, this is her periodic table, and I would like to dedicate it to her. Let's go back, though, 100 years to Mendeleev. And here are some of his first scribblings, which were leading him towards the periodic table. It's a bit difficult to see, but you can see here fluorine, oxygen, nitrogen, carbon, boron. He's clearly getting something in the right kind of board. There's fluorine, chlorine, bromine, iodine. He's getting some idea of the periodic table and the periodicity. When he published that in 1869, only 63 elements were known, and he included all of them in his table, and here it is. And you can see that it's not bad. It's not brilliant. It's not perfect, but it's not bad. And you can see a lot of the relationships, not in the direction we normally see them, but you can see them here coming along. And you'll see gaps, which I'll come back to in a moment. If you go to St. Petersburg, there is a wall chart of 1876, just 7 years later, which is on the wall. Here it is a bit more closely, and that's got that same information now in a kind of periodic table, which we begin to start to recognize with the groups going downwards like this. Now, in 2014, Alan Aitken, who was a colleague of mine in St. Andrews, was clearing out under a lecture theatre in St. Andrews, and he came across a whole lot of rolled up wall charts. And one of them was this. And it turns out, well, we'll see in a minute how we know this, but it turns out to be the oldest known printed wall chart in the world. It was found in 2014 by Alan Aitken. The university decided it was important, so they had it conserved in 2018, and it was available for display in 2019. I see, not 2108, that's a bit odd, isn't it? It was available display in 2019, which was the International Year of the Periodic Table. Now, Pilar Gil, who's a postdoc chemist, but also works in special collections sometimes. She has a master's in museum and gallery studies, researched this between 2018 and 2019. And what she discovered was that it was printed in Vienna in 1885, so just 16 years, 16 years after Mendeleev first wrote down the periodic table. It was purchased by Professor Purdy, who was a professor in St. Andrews, in 1888 from a German supplier. It's marginally different from the original Mendeleev table because gallium and scandium have been added. They've been discovered. That's gallium and that's scandium, but you'll see here a gap for germanium. And this helps us identify the age of the table, although she actually found the dockets that refer to it and the order for buying it and so on. So there's no doubt about what it is, it's a wonderful thing. But it isn't really what we expect to see in a periodic table. I think if you go into a lecture theatre in Lausanne or any other of the chemistry departments in Belgium, you'll find a periodic table which looks something like this. Although not this actual one, because this is a very special periodic table. This is made from macrame, which is an ancient knot tying craft. And this is made of 200,000 knots. It took Jane Stewart 350 hours, and she did it as a celebration of the International Year of the Periodic Table. And it has all of the modern symbols for the newest elements down here. It's a fantastic thing. And of course, the periodic table, if you talk to someone in the street about the periodic table, they may say, oh yeah, I vaguely remember that. That was some kind of chart hanging on the back of a chemistry lab, I think, and it smelled a bit, and I didn't like it much. And so it doesn't mean very much to them. It means a lot to us, of course, because as chemists, we can work out so much from it. We can work out what's going to react together. We can predict products, predict the properties of compounds, and we can use it really to design the whole of chemistry. And of course, we know that if we, these elements here have one extra electron compared with the noble gas structure over here. These have two, these have one less, these have two less. And we can predict, therefore, that if we take magnesium and oxygen, the oxygen will take 2 electrons from the magnesium, and we'll get a violent reaction, which indeed we do with magnesium burning in air here. But we felt that we wanted to make a periodic table that actually people would think about and look at and say, wow, what's that? And try and understand something about it. And this is what we came up with. And this is a periodic table which has, and it's not like anything you've seen before, it's quite different, but it has a number of very important messages. And I want to tell you about these messages. The first one is in the title, the 90 natural elements that make up everything. It's an astonishing thought that everything in our beautiful world is made up of just 90 building blocks, these 90 elements. There's nothing else. Put them together in different ways, different combinations, and you get everything we have around us in the universe. It's a fantastic thing. But because there are only 90 of them, it means we've really got to look after them, because if we don't have some of these, then what's going to happen? So the area then occupied by each element is proportional to its abundance in the Earth's crust and in the atmosphere. So there's lots and lots of oxygen, but very little iridium, for example. This is on a logarithmic scale, because if it were on a linear scale, you simply wouldn't see the elements down here. And then the color tells us about what we're doing to these elements. If we carry on the way we're going at the moment, using the elements, say in a phone, chucking the phone away or not getting rid of the phone, we will gradually disperse these elements around the globe in a way that they cannot be got back. And this means that if we're not careful, we're not going to run out of them, but we are going to find that their amount goes down and to a point where they're going to be very difficult to get hold of. And the red ones here, that's going to happen within 100 years, and we'll see in a minute, very much sooner than that in some cases. Orange, as we use them more, there's a bit of an increased threat. And then the yellow ones are some limited availability. The green, more or less plentiful supply. Then you'll notice 4 in black here, with 4 with grey shading. Now this grey shading means that they can come, they're tantalum, tungsten, gold and tin, that they can come from mines where wars are fought over the mine, or the proceeds of the mine are used to fund wars. So they're called, those minerals are called conflict minerals. Now they don't only come from those mines, but they can come from those mines. Just before I leave the question of colour, the other thing I want to say is about Robert Parker. We had this thing all set up. We presented it at the European Chemical Society meeting in Liverpool in 2018. And then Robert put his hand up and he said, "Are you sure these colours can be seen by colourblind people?" And it turned out they couldn't. This is not the one. There were different colours. We had to redo all the colours, and Suzanne again did this for me, so that these should be, if you have colour blindness, then you should be able to see every colour in this periodic table differently. And we had various people help us with that. Finally, on this periodic table, you'll see there's this symbol, which is a symbol for a smartphone. And this is the 31 elements which are contained in most smartphones, or almost all smartphones. Some have more, but most of them have all of these elements in. And you'll notice that all 4 of the elements that can come from conflict minerals are in a smartphone, and 6 of the red ones, which are going to run out within 100 years, are also in a smartphone. So I'm going to say a little bit more about that in a minute. But what this tells us is that we really do have a problem. We really do have to protect these elements and do something about it. What we have to, and I should say this is available in 30 different languages. And because I'm talking to you in Belgium, it is available in Dutch, call it Flemish, and it is available in French, call it Walloon. So we have this in more than 30 different languages. Now, what do we do? How are we going to, first of all, let's talk about these conflict minerals. What are we going to do to make sure that people don't use them? And there's this thing called traceability, where you trace the element from its mine, where it's mined, through all its processing steps, and then until it comes to you as a manufacturer of a mobile phone, you're going to put it into your phone. And they do that. Mobile phone companies do that, and they're very good at doing it, and they make sure that they don't get these elements from places which are from conflict mines. But let's look at tantalum. Tantalum is both a conflict mineral, and it's got less than 100 years to go if we carry on using it as we do. It's used in microcapacitors. Here's a microcapacitor. And these are used to stop surges in electric current, particularly in mobile phones. And every iPhone has at least one of these tantalum capacitors, which controls the electricity in the motherboard. 40% of world production comes from conflict minerals. That means 60% doesn't, and most of the rest of that is in Canada, so we can use that. But even with that 40%, there's less than 50 years left to go. So smartphones have been very good. They've been very good at not getting it from the mines in the Democratic Republic of the Congo, which is where the conflict mines are. But as it gets scarcer, temptation increases, and with them we have to worry about this. So the other thing we have to do is we have to think about how we use these things. I tell you that, if we just use and chuck away things, we're going to disperse it. So we must reduce our use. Now, you will get a phone call every 2 years, probably saying your contract's up on your phone, you're due a new phone, come get a new phone. And you probably go and get a new phone. But you don't need a new phone. You wouldn't need a new phone until 5 years are up. So just say, no, I don't want a new phone. And you will save not only elements, but you will save money, because you will then get a contract where you don't have to pay for the rental of the phone anymore. If something goes wrong with your phone or any other device, then you should have it repaired. I'll give you an example. We have a dishwasher in our house, and the catch that holds the door shut broke. So I phoned up a chap, and he came and he said, well, I'm not sure about this, he said. And he said, well, I can't get a new catch, so you're going to have a new machine. And I thought, no, the machine is perfectly fine. The door just doesn't shut very well. So fortunately, I was able to go online, find the catch, put it on myself for about £5, and end up with the machine. And it's been lasting for another 5 years since then. So repair things. Don't just replace them whenever they run out. When you have got to the end of wanting to use them, so when your phone becomes a bit, you need a new phone because it's got better things that you can do on it, then pass it on to somebody else. Pass it on to a child who needs a phone, or a grandparent, or even a sister or a brother or something like that. When it finally comes to the end of its life, then recycle it. And I'm going to say more about that in a moment, but that's very, very important. And down here I have replace. I don't mean replace the phone. I mean replace. We as scientists need to work on replacing the materials in the phone. So we have to try and make materials in the phone which are not from these endangered elements, the ones which we're going to run out of. And so we need to use earth-abundant materials, and we'll talk a bit more about that in a moment. So let's look a bit more at phones in detail now. And this is an astonishing figure here. In the European community, people upgrade their phones so that there are 10 million every month. That's not year, every month. It's 1 million in the UK, it's 1.5 million in the UK, it's 10 million in Europe, 12 million in the United States. It's a fantastic number of phones. And the question is, if you do that, if you get the call and you get the new phone, what do you do with the old one? Well, most people put it in a drawer and leave it lying around somewhere. And I bet you, most of you who are listening to me, have somewhere in your house a phone in a drawer. And if you have, the elements in that phone are completely unavailable to everybody. Nobody's going to send a digger into your house to try and dig a phone out. So this is a concern. The Royal Society of Chemistry did a survey, and they discovered that 51% of households have at least one mobile phone lying in them. If you do hand it in, what usually happens is they go to the developing countries where they're reused, which is a good thing, but then they're trashed or mined by children in the street using strong acids just to get the gold. And it's really dreadful the way they do it. And then the carcasses pile up by the side of the road. This is an appalling example of terrible waste in our society and a terrible environmental problem that comes from it. The other thing is that mobile phone companies make phones that are very, very difficult to repair. They make them using special screws, which you don't have the screwdriver. They make them using special glues, which are very difficult to break open. So if you need a new battery, you need a new screen, it's very difficult. You can get it done by specialist companies, but it's very difficult. They want you to have a new phone. They also build in redundancy so that after that 2-year period, your battery may not be working very well. It could be working fine. It should be working fine, but they build in so it doesn't work so well. So we need to have modular phones like this Fairphone where the parts can be replaced. Now, when you know all this, can you really justify changing your phone every 2 to 3 years? We have to reduce our use of mobile phones. So let's talk a bit about indium, because indium, we talked before, it's red in the periodic table that I showed you. So it's got a lifetime. We'll see in a minute what the lifetime is. It's used in flat panel displays. Indium tin oxide is the conducting film in touch screens. So when you touch the screen, you're touching indium tin oxide, and that's what sends the current through this screen. About 56% of it is used in that application, and there are other very important applications for indium. If we go on using it as we do at the moment, or I should say it's a byproduct of zinc mining. You don't have specific indium mines. You go to zinc mines and you get indium out of them. And if you look at the annual demand and the world reserves, it's very simple to see that the lifetime, using it the way we do at the moment, if we don't recycle any of it, is only 20 years. And that's really pretty shocking, and it becomes much more difficult to extract and the price rises. So, as I say, we have small amounts of indium tin oxide in every screen. We must recycle that. And then we need better companies, bigger companies. We have some companies which do ethical recycling, but we need more of them and bigger ones. And then we need to have proper incentives so that you will hand in your phone, not stick it in a drawer. In terms of replacing the elements in the phone, indium tin oxide, a lot of work is going into trying to replace it. And some of the examples here, graphene, antimony stannate, and calcium molybdate, they're coming on. This one probably won't be. This is blue, so it may not work, because what you have to have is you have something that's conducting, transparent, and sticks to glass. And some of these don't do that. And so really, indium tin oxide is perfect, but we do need to get other ones which will do it, which don't contain these rare elements. And it requires a huge amount of research effort. And then, as I say, you need to change your phone and computer less often. Now, I've been talking for, I don't know, a quarter of an hour or so, and I know your attention span is only about 3 minutes because you were brought up on Sesame Street, and Sesame Street knows that, and it only has things that last for 3 minutes, and then it has an advertisement. So I'm going to break for a moment now and give you an advertisement so that you can just switch your mind around a bit. And I'm advertising a video game that we developed for the International Year of the Periodic Table. The European Chemical Society developed it. It's a video game about chemistry, and it teaches you some chemistry. You have to solve puzzles, and it's really great fun. So after this, when I finished, get your phone, get your computer out, and download from this link here this video game and enjoy it, because it really is good fun. Right, now we come back to the periodic table. I'm going to talk about two other elements, lithium here and cobalt here. And I'm going to do it because they're very, very important. These three gentlemen won the Nobel Prize for Chemistry in 2019, John Goodenough, Stanley Whittingham, Akira Yoshino, for the development of lithium batteries. And I thank Nicholas Amaroli for these slides I'm going to show you now. Now, lithium is in the conducting part of the cathode of the battery. There's a lithium electrolyte, and it's in the cathode. So lithium batteries have a large amount of lithium in them. And lithium is wonderful. It's the lightest and smallest metal. It has a very high electrochemical potential. These are all good things if you want a portable battery. It has high energy density, high charging speed, and this a long duration, which makes it perfect for batteries. So it's a very important element, and we are going to use a lot of it as we move to more lithium battery electric cars, for example. And then in the cathode, it's not just lithium. We have cobalt and other elements as well. But let's talk about lithium first. The reserves are 16 million tons, although the resources are 63. So the amount you could get is 53 million tons. The main suppliers are Australia, Chile, and Argentina. But the biggest resource is in Bolivia. And I think Bolivia is going to become very, very important because the amount of lithium it has in this lake here. It's used, as I say, in the battery of mobile phones and cars. Here it is in the car. And the number of cars sold worldwide is 80 million. Now, if you wanted to replace every single car with a lithium-powered car, the amount of lithium you would need is 800,000 tons of lithium. We currently mine 80,000 tons a year. So that's 10 times more you'd need. It's there in the world. There's not a problem with the supply, but we just don't have it yet mined. So there's a lot of mining that has to be done. And it's really important that we should recycle it. It must be recycled. Cobalt, which is again in the cathode, as I said before, is much more critical. Now, cobalt is orange in the periodic table I showed you before. And here's the problem. The problem is that most of the cobalt comes from the Democratic Republic of the Congo. I've already said there are conflict mines there, although cobalt is not classified as a conflict mineral because it doesn't come from the big mines where wars are fought. It comes from very small artisanal mines like this, often tiny little shafts that people go down, run by individual families, and the children go down and work there. And it's a terrible conditions these people work under. So it's very, very difficult. We have to be very, very careful about cobalt. Now, what about this recycling business? I've annotated the periodic table again here, and what I've done is I've added different colors for how we're doing in the recycling. So if it's pink like this, almost none is being recycled. If it's blue like this, more than half is being recycled. And let's look at the elements I've been talking about. I've talked about tantalum, hardly recycled at all. I've talked about indium, hardly recycled at all. I've talked about lithium, hardly recycled at all. I've talked about cobalt, but now cobalt is recycled. So that's good, particularly as so much of it comes from the Democratic Republic of the Congo. But we really have to improve this. So if you want a job, if you want to make a fortune, get there and get out and get recycling these types of materials. I want to say just a word or two now about helium as my last example, because helium is very, very important. Helium is used to cool the magnets in MRI images. So this is an MRI imager. This person's going in, they're going to have an image taken which will look like an X-ray but doesn't involve X-rays. To do MRI imaging, you need a superconducting magnet. And the superconductor has to be cooled below the temperature of liquid helium. And that's why you use helium to cool. Another main use of helium is in deep sea diving, because if you breathe air in the deep sea, nitrogen in the air dissolves in your blood, forms bubbles. Oh, it doesn't form bubbles then, but when you come up and the pressure goes down, the nitrogen comes out as bubbles. It can cause nitrogen narcosis, sometimes called the bends, and you can die from it. It's a really big problem. So what you do is you dilute some of the nitrogen out with helium. You mix helium into the mixture, take some of the nitrogen out, and then you can safely dive at deeper sea levels. You still have to do your stops on the way up, but helium doesn't dissolve in the blood. And that's why, of course, divers have squeaky voices, because the helium has the speed of sound in helium is higher than it is in helium. Once released into the atmosphere, and this is the big problem, if you let the helium go into the atmosphere, what happens is it goes up and up and up and up and up, comes to the edge of the atmosphere, and then it's knocked into outer space forever. So it's lost forever. And it's the only element we lose. So that's very important. But the good thing is that in these two applications, the helium is recycled. Here's somebody wearing a rebreathing apparatus for deep sea diving, and that recycles the helium. Here's a recycling apparatus for an MRI scanner. I'm not going to go through it, but it is recycled. Now let's look at the supply of helium. There are three main suppliers, one in Qatar, which is closed, one in the United States, which will close in 2021, and a new one in Tanzania, which is opening this year. The amount in the Tanzanian field is enough. If we just used it once and discarded it, it would be enough for only 8 to 12 years. So there is a potentially serious problem with helium if we don't recycle it. And the one place where we don't recycle it, of course, is in party balloons. If you have a party balloon, it will go down or it will pop. The helium will go into the atmosphere. It will go through the process I've described to you, up and up and up, till it gets to the outer atmosphere, and then it gets kicked out into outer space forever. When you know that, can you really justify using helium celebration balloons at a party when it will be lost forever? Now, I've been talking about this for about a year now, and writing articles in newspapers and appearing on the radio. And the helium people don't like me very much. And they're very keen to tell me that they don't like me very much. And they write to me and they say they're going to threaten me with all kinds of things. And one of them, the European Balloon and Party Council, wrote to me and sent me their fact sheet saying, look, this is the facts. You're talking nonsense. We're perfectly fine. We don't do any problem because we only use a tiny amount of helium in party balloons. When you look closer into their own fact sheet, it says it's 10%. So a tenth of all helium goes into party balloons, not a tiny amount. And I did a program on a Russian television channel, not one which is independent of Mr. Putin. And in fact, the head of it opposes Putin. And in that program, I couldn't understand it because it was dubbed into Russian, but my friend from Kazakhstan told me that it said that 47% of all helium in Russia is used in party balloons. Then these people said, well, it's dirty helium and it can't be recycled. It comes from MRI scanners, but it can't be used in scientific and academic applications, and it can't be really liquefied or purified. It's uneconomical. Forgive the grammar here. It's their grammar, not mine. And it's uneconomical. It can't be done. But then when you look closer into their fact sheet, it tells you that the helium must be at least 95%. The helium in the Tanzanian field is less than 10%, and we're going to purify that. So surely we can purify this. I think it's nonsense. And if you then work through the figures a little bit and think about it, I've told you that if we use the stuff in the Tanzanian field once and discard it, there's 8 to 12 years. If we use 10% of it and do that, we will get rid of it all in less than 100 years. That's shocking. That means in 100 years' time, your grandchildren won't be able to have MRI scanners, at least not using the technology we use at the moment. So this is very serious. And I think when you know that, you really can't justify using a helium celebration balloon. And it's even worse than that, because helium balloons, if they get away, they can get caught up in the rail lines and stop trains, and they can be dangerous. And in 2018, there were 619 balloon-related incidents, many of them dangerous. And of course, also, the balloons are made of plastic. Here's one that was found on a beach in St. Andrews. And the plastic goes into the environment. And if you look online, you can see tragic pictures of calves that have swallowed helium balloons and choked and died. Dolphins will swallow them, other sea mammals. Now, then the balloon people will tell you, but they're biodegradable. And that's good, of course it's good. But it takes a few months for them to biodegrade. And they can be swallowed in a few seconds by an animal, and that's the end. So this is a really very, very serious problem, and they really have to be banned. And even the balloon people understand that, and they're trying to make paper balloons. But there's some good news. Gibraltar, which is, as you know, an island off the south of Spain in the Mediterranean, has a national day every year where they used to release tens of thousands of balloons, red and white, because they're the national colors. These are helium balloons. And in 2012, it was banned. And it was banned partly because of the helium, but also because of the plastic. Gibraltar is surrounded by sea, so all this plastic went into the sea, and many people, and many dolphins and sea creatures swallowed them and died. So they became aware of that, and they banned it. So you can have an effect, and we should have an effect. Another interesting good news story concerns the lanthanoids, which are this lot down here, also known as rare earths, which are used to make the colors in your telephone screen, in your phone screen. And here's some colors that you get from them. And they used to be considered vulnerable and very dangerous, and we were going to lose them. But in fact, in 2018, a very large supply was found in the sea off Japan. So they're not really on the danger list anymore. The one that you'll see there that's different from the others is dysprosium, that's it there. And that's because it's used in windmills for their magnets. And as we make more and more windmills to harness more and more of the wind energy, then this could become a potential problem in the long term. But this is a good news story. So I come to the end now, and these are my take-home messages. Your country needs you to keep your phone for longer, to hand it in when it's at the end of its life, and never to use helium party balloons. Let me leave you with a thought, a question. Why can you never trust elements? Because they make up absolutely everything. Thank you very much.
Thank you very much indeed, David. We had decided that we would try and ask a few questions at the end, but I'm going to ask the questions because we're still in the learning stages of this technology, and I hope that when we get further on, we'll be able to do this directly with the people linked in. So my first question, which is a rather philosophical one, but I'm glad to hear that the lanthanides are not a problem anymore, because this was one of the examples which I consider to be quite serious of dumping on the part of the Chinese, to be quite blunt, to bring down prices, and then they introduced an embargo. Would you like to comment on that?
Well, yes, indeed. I mean, one of the good things about the new find is
David?
Can't you hear me?
Yes, indeed. I mean, one of the good things about the new find is that, can't you hear me?
Yes, we can hear you.
Yeah, one of the good things about the new find is it is in Japan, and Japan is a country where I think
The new find is it is in Japan.
the problem that I'm still
Japan
sharing.
is a country where we
Here we go. Sorry. I seem to be very slow in getting through to you. Here we are.
Could people cut their video, please? Could you please cut the video? Because you.
Yeah. Okay, can you hear me?
Could people whose pictures are appearing on the screen please cut your video?
Okay, can you hear me?
Yes, I can hear you now, David. Rita, yeah, go on, David.
Oh, yeah, I think the answer to your question is the good thing about the recent find in Japan is that Japan at the moment
The good thing about the recent find in Japan is that Japan at the moment
there's something very wrong with the sound, is there?
Okay, try again.
Right. Can you hear me? Is that any better? I think I'm trying to speak to you, but I don't know whether I'm succeeding. Well, anyway, what I'm trying to say is that because Japan is a country we can do business with, I think the supply of lanthanides is reasonably safe now, and the Chinese can't do the same thing again.
That's good to know. When it comes to recycling, okay, people can hand in their mobile phones just as people can hand in their batteries. How do you think that the helium business is going to end up? I mean, the balloon manufacturers are probably not going to stop selling helium to fill balloons.
Well, they will do. It's not really a question of the balloon manufacturers. It's a question of the people it's more a question of the people who supply the helium in the first place, because they really should be responsible for the recycling of it. So they should take it back from the MRI scanners. They should purify it. And it should never go to the balloon people. And the balloon people actually now are beginning to say, yes, we can now do things with paper and air, and we can make very nice montages. And I think they are beginning to appreciate that helium is not really appropriate for them to use in that way.
So that you think that will solve the problem, at least because obviously the NMR and the diving applications, there is constant recycling going on there.
Yeah. But I think also in the end, if they don't do it, we may have to have legislation to do it.
But then, of course, we have to make the legislation stick. So the worrying thing about cobalt, because obviously it's something which interests us as biological chemists as well as other things, is that most of the cobalt is coming from a very insecure part of the world, because I mean the Belgian Congo has been something that's been fought over for the last almost 100 years since we started exploiting the mining in there. Is there any chance of finding other sources of cobalt?
Well, there are some other sources, as I showed. There's some in Canada and some in China, but the vast majority is in the Democratic Republic of the Congo. And I think that the good thing about cobalt at the moment is a lot of it is recycled, and we have to get on and do more of the recycling of the cobalt.
Yes, because unfortunately, one can predict as well as one might, but the area of Katanga in the Congo is not going to become something that's not going to be fought over in future years, I'm afraid. It has a bad history, going back to the time when Belgium tried to get rid of it. It's not been a very successful story. Yeah. So I think that with that, we will draw this evening to a close. I would like to thank you once again for joining us and putting up with all the little quirks along the way. And thank you for being willing to give us a hand in running through things ahead of time. I'm glad to tell you that you will be receiving a small gift of our appreciation, which we have been able to source locally. So you will find that it's somebody in St Andrews is going to come and deliver it to you. And I shan't say any more, but it will be eminently consumable, and I trust it will not last too long on your shelf.
Before you go, Bob, before you go, I just want to show you.
Right. So let me just, yeah.
To show you.
Yes, I thought you might be prepared to do this. We were asking about this on Tuesday when we spoke earlier. Yes.
On full screen, but there we are. There's the T-shirt that you were asking about. Okay.
You showed at the Liverpool meeting. Yes. Well done, sir. Thank you very much again. Thank you all for joining us this evening. I remind you that our next event will be on the 10th of November with Brigitte Van Tiegelen talking about women in science. And we will keep you posted about Nick Lane's lecture, the AGM, and the Café Chimique, which will be coming up in February. Thank you all once again. We look forward to seeing you on the next event. And we hope that as we go along, we will gradually be able to get things in a more interactive mode than we have this time. And David, once again, all our very best thanks to you. And we look forward to having the opportunity of offering you some proper Belgian hospitality next time you're in Brussels.
Thank you very much for inviting me to your